Hello and welcome to our 43rd session. In today's session we're going to be working mostly on the Deal-Grove model of thermal oxidation, and then we'll be tying up some loose ends. We'll be looking at a graphical model of something called threshold roll-off. We'll see what that's all about, and then we'll be reviewing the evolution of the Q inversion and the IV characteristics for the simple model all the way up into the more sophisticated, improved models. And hopefully, if we have some time, we'll be doing some examples. If not, we'll do some examples in our next session. We'll start off with a video clip from the opera Barber of Seville, Una voce poco fa, and we'll see you in about 4 minutes.
Ma se mi trovo mio demone sarò, non viverò, sarò, e 100 trappoli prima di cedere farò giocare, e 100 trappoli prima di cedere farò giocare. E c'è da trappoli prima di cedere, e 100 trappoli farò giocare. Io sono docile, sono obbediente, mi lascio reggere, mi fa guidare.
Welcome back. These are some of the topics we'll be covering in today's session. We're going to work our way through the Deal-Grove model of thermal oxidation, and then we'll be tying up some loose ends, and if there's time we'll go into some examples. If not, we'll leave it for the next session, and we'll end with the marvelous soliloquy from the musical carousel. Okay, so this is a continuation of our discussion of the Deal-Grove model. Here we see wafers which are being loaded into a thermal oxidation furnace, kept at over 1,000 degrees. The range is somewhere from 900 to about 1,100 centigrade. So let's look at the following. This is kind of a rough cartoon of what's going on here. The ambient temperature, that's when they're out here. Once they get into this so-called static layer. Static layer is kind of like an antechamber. The thickness of the static layer stays more or less constant throughout the process. When they get to this interface, then they encounter the growth layer. This is solid SiO2. And this changes. So at the beginning, Tox is essentially 0. And as the process continues, Tox increases. At each step along the way, there is a partial pressure of oxygen molecules, or a concentration of oxygen molecules, and that must of necessity decrease because it is the concentration gradient which forces the process. So CS is less than C0, CS is less than CG, C0 is less than CS, and CI, when the molecules finally get to the promised land, this is the silicon surface, and CI is the lowest of the concentrations. Okay, this is a rather interesting interface right here, and there is a sudden drop from CS to C0, and at this particular interface, there's something called Henry's Law, which applies, and we'll talk about Henry's Law in some more detail later on. There are 3 fluxes. F1 pushes the oxygen molecules into the static layer. F2, they diffuse through the static layer into the growth layer. And F3, they actually convert from, well, I shouldn't say convert, the chemical reaction O2 plus silicon goes to silicon dioxide. So just a word about these things called fluxes. Fluxes always represent stuff per second per square centimeter. The question is, what is stuff? We're going to define stuff, in this case, as the number of molecules per square centimeter. So it's the number of molecules per square centimeter per second. That's going to be our flux. That is exactly analogous to the electrical flux. In the electrical flux, it was charges, could be number of charges or the charge itself in the coulombs per square centimeter per second. So you see the actual analogy here. It's really quite reasonable. Instead of using number of molecules, we could say the grams per second, per centimeter square per second, but then would make the units come out a little bit more complex. So we prefer to say just the number of molecules per square centimeter. Of course, it's a huge number. So this number, N, is, we're going to call it N, is going to be quite large. Now, the critical thing about this diffusion process is that it is not an equilibrium process. We know it's not an equilibrium process because material is moving. If it was equilibrium, specifically material equilibrium, then nothing will be moving. Of course, it's also not thermal equilibrium because here we have essentially out, well, to the left of this region here, we have room temperature. Once the wafers are loaded into the furnace, the temperature becomes quite high. So it's not in thermal equilibrium, and it's also not in material equilibrium. So this is exactly analogous to what we have if we have a battery connected to in silicon. This arrow points to the motion of the electrons. The little black circles here are electrons. Electrons move from right to left. The electric field is from left to right. And we have a situation where we have material non-equilibrium. If material non-equilibrium means that the Fermi level is tilted, the lower part of the Fermi level represents the positive voltage. The higher part of the Fermi level on the right side represents the negative voltage. So that's pretty straightforward. We've seen that quite a number of times. That's one of the simplest cases. Now we look at another case where there is diffusion current. Here there is only drift current. There is no diffusion current. And we know there's no diffusion current because the Fermi level position with respect to the band edges doesn't change. So the concentrations at the left end are equal to the concentrations on the right end. However, if we look at the neutral base region in a PNP bipolar junction transistor, we have more holes, excess holes on the left than we do on the right, and therefore we have a diffusion current from left to right because delta P1 is greater than delta P2, and that's what we're saying here. The left side is more P-type, the right side is less P-type, so we have a diffusion current. We have no electric field because EC and EF are horizontal, but we do have material non-equilibrium because stuff is moving. Okay. However, there is one significant difference between thermal oxidation and the situation of the bipolar junction transistor. In the bipolar junction transistor, the BJT, if it's in the forward active mode and we don't change the voltages and keep it on, this thing continues basically forever. We're always injecting more holes from the emitter into the base, and those holes are collected at the base collector junction. In thermal oxidation, that is not the case. We're going to see that we have diffusion until we get to a point where the oxygen molecules just cannot diffuse anymore. The T-ox, the gate oxide or the oxide thickness in the growth region becomes so large that diffusion stops. And that would be analogous to if we have a perfume bottle and we open up the bottle and the perfume exists to a rather large concentration at T equals 0 on the left end, and it diffuses throughout the area till eventually it fills up the entire space. So instead of using Fermi level, we use chemical potential. So what happens, the chemical potential initially is tilted, which drives the perfume from the left to the right. But as the perfume spreads out, the chemical potential now moves and the tilt goes away so that for a large time, T much greater than 0, the chemical potential becomes horizontal and the diffusion of the perfume ceases. So that's a better analogy to what we have in the thermal oxidation process. Okay, so let's now analyze this thing a little bit more in detail. And the first thing we require is that the three fluxes be equal. F1, F2, F3. Just to remind ourselves, these way back here, this is F1, F2, and then F3 is when the oxygen molecules reach the promised land, the interface between the glass and the silicon. So if they weren't equal, we'd have stuff piling up. That's not good. So we require that the three fluxes be equal, and then we're going to examine each one in somewhat more detail, but keeping that in mind, and we'll use that later on. So let's take a look at F1. F1, again, I should probably redrawn it. F1 is what happens in here. Cg must be greater than Cs. It is a diffusion process of oxygen molecules through the stagnant layer. If it's a diffusion process, we can write it as some diffusion constant divided by some thickness. That is exactly what we had in the case of the BJT. In the BJT, the Cg and Cs are delta P1, delta T, delta P2. T1 is the diffusion constant, and T sub SL becomes the width of the neutral base region. So it's exactly analogous. And what we're going to say is that TSL, the thickness of the stagnant layer, does not change, so we can combine D1 divided by TSL into one constant, which we call Hg. So, if we look at the units, again, the units of F1 are number of molecules divided by centimeters squared second. The units of C, whatever C is, are the number of molecules per cubic centimeter. So the units of H are centimeters per second, I believe. Okay. We could have written this in terms of partial pressures. Partial pressure being the pressure of the gas, the molecules, the oxygen molecule, in the gas. So if it's air, it's 20% oxygen. So if it's atmospheric pressure, it would be an atmosphere divided by 5. But we're going to use this a bit later on because we've got to put in temperature. Temperature is a very important parameter. But for right now, we'll leave it in terms of equation 2241. And again, the units of Hg are centimeters per second. It's a velocity, and that's what makes the units of F1 number of molecules per square centimeter per second. Okay. So the flux F2, before we go into F2, I just want to make one more point about F1. This is really analogous to a neutral base region in a BJT. We have a constant value here multiplied by a differential gradient of concentrations producing a flux. Okay, so let's go back to the original picture before we trudge on to F2. Let's see, back here someplace. Okay, this is the F1. This is one where we have a constant coefficient in front of the concentrations, whereas this guy, which will be F2, we have a variable coefficient because Tox is going to change, is going to grow. And this is the critical interface right here where we take oxygen molecules and we dissolve them into the SiO2 growth layer. Whether it's a liquid or solid, doesn't matter. We've got to push these guys here, where oxygen is a pure gas, into the growth layer, and hopefully they will diffuse according to F2 right here, and until they reach the silicon interface where they can form SiO2. So that's the idea. And now let's take a look at F2 right here. This D is going to be constant, but D over Tox is going to change. C0 is the concentration at the beginning, and Ci is the concentration at the oxide growth layer silicon interface. C0 better well be bigger than Ci in order for the growth to occur, in order for the oxygen molecules to get to the silicon surface. So this we can also compare to a BJT, but a little bit different. And what happens in a BJT as we increase the reverse bias along the base collector junction? What happens is I'm sure you remember, I hope, that the depletion region on both sides grows. We make the doping in the collector lighter so that hopefully more of the depletion region growth is on this side, but there's some growth also on this side, which makes the distance W less. The W decreases, which implies that current increases, and that is basically all we're saying here. As VCE grows, W decreases and J increases. For oxide growth, basically we start at a very low value. Could have some native oxide in the beginning, but generally we start from just about zero. And with time, the Tox increases, so the denominator increases and the diffusion decreases, eventually going to zero. Okay, so before we go on to the actual reaction itself, let's go back again and look at this interface right here between the stagnant layer and the growth layer. We're dissolving molecular oxygen from the gaseous phase into the liquid/solid phase. So what happens here at the interface is governed by something called Henry's law. And let's take a look at an animation which describes Henry's law right now. So this is the growth layer down here. This is the interface layer right here. These little blue balls are the oxygen molecules, and the idea is we press them in. And you see the higher the pressure, we're pressing down with a piston, the more likely it is for the oxygen molecules to be dissolved in the growth layer. And the relationship is given by the solubility of the gas, Henry's constant, we're going to call it big H, not K, and its important thing is the partial pressure of the gas. And here we write an expression for Henry's law. We call capital H the Henry constant. P sub S is the partial pressure in the gaseous stage, and C0 is the concentration of oxygen in the growth layer, and that's a big deal. So the units of C0 are centimeters to the minus 3. That's our concentration numbers per cubic centimeter. The units of pressure, of course, are force per unit centimeter per square centimeter. So the units of Henry's constant are, put all this stuff in, we must have centimeters times newtons, which is 1 over joule. So the units of Henry's are 1 over energy. Okay. Now we write the ideal gas law, PV equals NKT, where N is the number of oxygen molecules per cubic centimeter, K Boltzmann constant, T of course is the absolute temperature in Kelvin. N is a very large number, K is a very small number, and T is about 1,000 degrees centigrade. Okay, so we substitute that in for volume. For pressure. We get just NOV KT, and we've eliminated the pressure now. And now, what is N over KT? This is in this growth phase. So what we have here is just a concentration number divided by volume by definition. So we have an expression now for C sub S, which is what we want, in terms of C sub 0, H, which is fundamental constant, K, of course, is a fundamental constant, as is T. So one of the reasons that Henry's law is so critical, it allows us to introduce through the back door t, which is really an important parameter. Okay, so now we reduce the number of variables, and now we want to eliminate some more variables by doing some algebra, and it really isn't all that big. Okay, so here we write F1 again. This is the flux in the stagnant layer. And what's the variable we'd like to get rid of here? Well, certainly Cg is an important variable. That is the atmospheric pressure, partial pressure of oxygen in the atmosphere. So that's something we're going to carry through. But C sub s, not so great. So we substitute. So we take the basic equation, we expand it, and we make two substitutions. And these are not obvious substitutions, but if you substitute these values into here, you will see that indeed this equation is correct. F1 equals this constant H multiplied by parentheses Ca minus C0. So that works out okay. Now it works out okay as far as units. The substitutions are right on. Okay, the nice thing is that both Ca and H correspond to parameters that don't change. So these are going to be things we're going to be carrying through to the bitter end, and H is let's see, H, this is centimeters per second, so this is 1 over energy. The units of Ca are the units of Cg, because H times kT is 1 over energy multiplied by energy. KT is energy. So these units, in fact, this is unitless quantity right here. So the units of H are the same as the units of Hg. So it works out, the algebra works out, and the units work out. So that's a good thing. So now we have two unknowns, C0 and Ci. So we're not quite done yet. But we've got lots more tricks up our sleeve. We rewrite equation 248 again. Here it sits right here, remembering these constants. And that, of course, is equal to F2. And, of course, it's equal to F3 also. This is the original expression for F2 in terms of C0, which is the dissolved oxygen at the left side of TOX, and this is Ci at the right side of TOX. And, of course, it's divided by TOX, and D is the diffusion constant. Of course, D is a constant. So D is a fundamental parameter. TOX, this is the guy we're trying to find. So let's not lose sight of that. This is the result. So this is what we want at the end. And we're not done yet, because F2 has got to be equal to F3. And that gives us another relationship between the parameters and Ci. So now we have two more equations, and we can turn the crank, and we're going to solve for C0. C0 is something we'd like to eliminate. So we solve 251 for C0. Relatively straightforward. It's 252. We basically just expand the parentheses here, and we isolate now C0. Just bring C0 over on the left side, everything else on the right side, and then we multiply by TOX over D, which is here, and we get equation 253. This is simple high school algebra, nothing very complicated here at all. Now we have a little bit of a mess, and we again rewrite our not original equation, this equation here. That's this guy. which of course is equal to F2, so this is nothing new here, but we substitute in for C0, and that's the big deal. So we substitute for C0, and we substitute, basically just for C0 here. We have Ca, H times Ca minus C0. Here's C0, and we just stick it in, and then we continue, and we basically expand the parentheses, HCa minus HCI multiplied by this guy is equal to D. This is, again, F2. This should be Tox. Okay, so I fixed the Tox issue, and we have equation 2254 right here. And what do we want? This guy, Ci. Ci is the concentration of oxygen molecules at the growing Tox silicon interface. So I isolate Ci, and this is the equation that we seek. It may look a bit messy, but it's actually much easier than it looks. It basically says the number of oxygen molecules at the silicon surface is a function only of Tox. Everything here is a constant. Ca, H, Ks, D, they're all structural constants. So the only thing I'm really, the only variable here is Tox. What I really want, however, this is the equation we seek, but it's not quite there yet, because what I want is a differential equation which tells me how does the rate of change of Tox with respect to time vary. And once I have a differential equation for Tox in terms of all of these parameters, then I can integrate and get the time evolution of Tox. So that's my goal. And I can do that by going back to the fluxes. The fluxes have within them, buried within them, rates. Because what is the units of flux? They are numbers of oxygen molecules divided by centimeters squared second. So in here I have buried my differential equation. All I have to do is to extract it. And notice that I have Ci. So I've got Ci here, and that is basically it. So what do I do? I take F3 divided by N, and I get a differential equation which involves the first derivative of Tox with respect to T. And how do I know that? Because the units tell me. The units of F3 over N, F3 are numbers for square centimeters per second, that's F3. The numbers of N are centimeters to the minus 3, but because it's on the bottom, centimeters cubed comes on top, and it cancels out. Everything cancels nicely, so I get centimeters per second. That is a rate, and that is exactly what I want. So now I just substitute for Tox, and by just going back to equation 2255, and I basically just stick it in because this is F3. I just stick in F3 over N. I just stick in my Ci from 2255, divide by N, and that's it. So this is 2255 divided by N, which is equal to F3 over N, which is d Tox, first derivative of Tox with respect to time. So this is my basic equation. This is the equation I have to integrate. And what I do is I just bring over the denominator to the left side. And of course, then I bring over Tox to the right side and unintegrate. And that's all there is to it. And here is the differential equation. Basically, it's equation 2258, where I made a simple substitution for some constants here, constant here and a constant here, to get equation 2259. And this is the equation that we integrate. Again, this constant A involves only structural constants. There's no variables here. And when I integrate this guy, of course, I get a parabolic term plus a linear term, and is equal to just a function of t, and tau is the lower limit of integration. Tau would represent any initial oxide which is on the silicon wafer. So now all I do is I don't have to, but I can substitute in for any constants which I don't know, namely A and Ca. And notice that Ca, again, only involves structural constants and temperature and the initial partial pressure of the oxygen in the ambient atmosphere. So I can do that, and then of course I can substitute in for the parameter A, and also, if I want, I can substitute parameter H, which also involves only structural constants. This Hg involves the diffusion through the stagnant layer. H is Henry's constant. So everything is structural only. Well, if we go back again to 2259, the differential equation, I'm going to break this up into two parts. And the first part is when Tox is very small. And let's take a look at that. When Tox is very small, where is it? Okay, it's right here. So we can have only the second term right here. And I can eliminate the first term for very small Tox. And that is equation 2263. Here it is right here. And I substitute for A. Note that H in this case is much greater than K sub S. So I get a very simple equation for a differential equation for Tox, for small Tox, and it is going to be linear. When I differentiate this, I'm going to get a linear function of Tox with respect to time. And what that says, and this is important, for very small Tox, all of the oxygen molecules which reach the silicon surface have easy access to the silicon, and they all react. And their reaction depends only on the first order rate constant of the very simple reaction. Silicon plus oxygen gives silicon dioxide. The rate does not depend on D at all, because there is no diffusion through the growing oxide layer, because the oxide layer is so small. Conversely, for larger Tox, we take 2259, and we consider only the first term on the left. In this case, I have a parabolic relationship, and here I have strong dependence on the diffusion constant and the constant Ca. So we can summarize that in a overall growth figure, which shows Tox as a function of T for a function of time. For very small layers of Tox, we have easy access to the oxygen molecules to the silicon, and we have a linear relationship. As diffusion becomes more and more important, as the Tox grows, we have a parabolic relationship, which eventually flattens out so that the whole process stops somewhere along about a micron or maybe a micron and a half of TOX. So in this region, easy access of the oxygen molecules to the silicon. In this region, the oxygens have to diffuse through the growing layer, and the diffusion becomes more and more a limiting factor until eventually everything stops. And that is the Deal-Grove model. And one final point to emphasize here, it is strongly temperature dependent. If the temperature is room temperature, I don't even have diffusion. This is knocked out completely, and I just have this little area in here where the oxygen molecules have easy access to the silicon, and this growth rate, or not growth rate, but TOX here is somewhere on the order of 20 to 30, maybe 50 angstroms at the most, whereas here it extends out to, can be well over a micron, depending on the growth temperature. Okay, so the next topic is the what we call threshold, should be threshold voltage roll-off. We'll see what that's all about for short channels. And we're going to look at this as a geometric model. It's called the Yau model. So we start with a MOS structure. Notice no source and no drain. But at threshold, we have reached the maximum value for the depletion region. So this is the depletion region width here. And of course we have the gate oxide here, and we have the gate. So now we take the same structure, except now we put on a source and a drain. And the source and the drain are composed of degenerately doped N+ silicon. Now, why don't we use metal? Well, we have to go down into the silicon in order to have an intimate contact with the inversion layer. The inversion layer is right here at the top of the depletion region. So it's this very, very thin layer right here. And in order to contact that intimately, we have to implant into the silicon. Why don't we use P+ instead of N+? Well, because we need a source of electrons to support threshold. So when the voltage on the gate reaches threshold, we have to suck up a lot of electrons, and there just aren't that many in the P substrate. So the N source and the N drain represent electron-rich regions where I can form the inversion layer. So we always have to, we're required to. We don't have much of a choice about implanting an N+ source and an N+ drain. However, there is a downside, and the downside is that we have p-n junctions at the drain and at the source, because on the bottom we have a P, and on the top we have an N. That's a p-n junction. Now, as far as the depletion region or a p-n junction, the N+ will have extremely small depletion region because the doping density is so high. So the entire depletion region is going to be on the P side. So this represents an area depleted of charge. It is P-type, so it it's composed of negative fixed ions, generally arsenic or boron. So what we have here are three depletion regions. One due to the gate. This is a depletion region under the gate. This is the good depletion region. We need it. But we have other depletion regions at the source and at the drain, even if we have no source to drain voltage. VDS is 0 at both ends, in both the source and drain. And that produces a problem because this depletion region at both ends extends into the area under the gate, and that is represented by these two triangles. They're symmetric because VDS is 0, but they wreak havoc on the device performance. So let's examine that a little bit further in figure 2229. And what we see here is this is the border, the N plus demarcation right here. This is the implanted region, extends down to here, and it also extends into this region here. This is the original gate length L, and we have this extra region here, X, which now has to subtract from L. So this is the depletion region into and underneath of the gate. And what is represented here at the drain also happens at the source. So we have these two lines here which represent the depletion region as it extends into the depletion region due to the drain as it extends into the depletion region under the gate. So just for some distances here, this distance D, put on the left side, but it's also the same thing on the right side. It's the distance from this point to this point. It's equal to X plus Xj. So this is a little bit more detailed depiction of the Yau model. Now we have a effective channel length, L prime, which is smaller than L, namely it is L minus 2x, not minus 2D, but minus 2x. This is the depletion region as it pushes its way into the gate. Now the other thing is there's a relationship between WD max and WD, and this is WS is over here and WD is over here, but they're the same because they have the same dopings. Degenerately doped and then P substrate. WD max is given here. We've seen that many times before, and WD is given by this expression. They are the same except for a root 2. So if WD max increases with doping, then WD and WDS also increase. The doping is on the in the denominator. Larger the doping, the smaller the depletion regions. So now we have this triangle. We have D on the one side of the right triangle. We have WD as the other side, and the hypotenuse is XJ plus WD. And we can solve for D, which we do here, just by using the Pythagorean theorem, and we get the value X, which is the important value, because that's the value that's going to determine L prime, and this is an expression for X as a function of WD, the depletion region of the PN junction, and XJ. What is XJ? It is this distance right here. So for any L, doesn't matter what the L is, I'm always going to have a L prime which is less than L. Doesn't matter if it's long or short, doesn't matter what the voltages are. If we are threshold, I am going to have an L prime here which is less than the channel length L. And this is the D right here. Now that comes basically just from equation 267, and this is the sort channel effect. All of this stuff right here, and it ain't good. Addition, not even, it's bad, it even gets worse. If you apply a VDS, let's go back here, apply a VDS, oops, actually over here, if VDS is greater than 0, well, that is going to reverse bias this N plus P junction. Why so? It's N plus. If we apply a positive voltage here, it will attract electrons up, and it will increase the barrier, increase the depletion region, and WD will grow even bigger. And so if you could have a VDS greater than 0, this red line will go down. Of course, it will stay the same on the left side, but it'll go down on the right side, and this guy right here will actually move over, and it will make L prime even smaller. So that's, of course, that's a practical situation, which we always have, but it's certainly not good. So let's summarize these results in figure 2230. The ideal situation, of course, this does not involve a source and drain contact, would just be a depletion region, which has a width of WD, or in this case, it's a height of WD max at threshold, and we would have the full channel length L. If I have a moderate case, again, we're not putting on a source to drain voltage, so there is symmetry between the left side and the right side, so VDS is 0 in both of these cases. However, if I reduce the channel length L, so here L is smallish, maybe call this L1, doesn't matter. This is when we have a shorter channel length. If we have a shorter channel length, then we are going to get these depletion regions at the drain and at the source. They are symmetric, again, because VDS is equal to 0, and L prime is less than L, so I have less control of the what happens underneath the gate has less control about what happens underneath the gate, and that's a very severe performance detractor. And if I have a really small L, what is ideal with these things will be a little bit of a actually it would be the same triangle here, but its effect would be extremely small if we have, say, a 1 micron gate. But if we have, say, 0.4, 0.5 micron gate, we're starting to see this effect. And if I have a 0.1 micron gate, notice that the triangles here are the same widths. This X here is the same as the X here, but the effect is much, much greater. The L prime here is much larger than the L prime here because the L is much smaller. So this is going to be a severe short channel effect, and this is going to be only a moderate short channel effect. We could probably live with this one. We probably cannot live with this one. So what happens is that there is a threshold roll-off. We have to apply a greater gate voltage in order to achieve threshold. And in the ideal situation, this again would be about a micron, half a micron. As the L becomes smaller, the threshold roll-off becomes more and more severe until we get to a point where the device is really, really suffering. And finally, I can define a figure of merit. The figure of merit would be basically the areas of the ideal versus the area of the trapezoid, the non-ideal. And I can basically just take out the WD max because it appears to be the same value no matter how severe or moderate or ideal the effect is. So it's just basically the trapezoidal area, which is L plus L prime, divided by L. So the area of a trapezoid is the average of the two lengths, the two sides, up and the down, the top and bottom side, divided by 2. So all I do basically is stick in my L prime. So it's L, which is here, plus L prime. This is the L prime that we found from equation 2269. Just put that in, and I simplify, relatively straightforward, and I get the figure of merit is given by equation 22, this should be 22.7. And what we see is we want to make this effect as small as possible. We want the figure of merit to be as large as possible. How do we do that? Make L big? Well, we can't really do that because we're pushing smaller and smaller L's. We make xj as small as possible. Let's go back here. The way we make xj as small as possible is we have as shallow as possible implant. Instead of implanting all the way down to the solid red line, we would like to implant way up here and make the source and the drain depths as small as possible. So that would be one way to do it, and that is one of the things we actually do. We have a narrow source and drain depths by using a shallow implant, but the other thing we have to do is to decrease the depletion region width. How do we decrease the depletion region width? Well, this is the bottom line of the whole exercise. We decrease the depletion region by increasing the substrate doping. The higher the substrate doping, the higher the concentration of holes in the P region, and the lower or the smaller the WD. And that is a really, really important thing that we can do. And remember what we said for the M, or this business of M, we like to have the doping as low as possible. This overrides that. And this says we want to decrease the depletion region by increasing the substrate doping. Okay, so we will take this up in our next session, finishing up by the evolution of the Q inversion and the IV characteristics. This will be pretty much a complete review of everything we've done in MOSFETs, and then we'll have some worked examples from chapter 23, and we'll end today's session with the soliloquy from Rodgers and Hammerstein's Carousel. In the soliloquy, Billy, who's been a terrible husband to Julie, is informed by Julie that she's pregnant, and finally Billy realizes the responsibility that's going to involve in him on being a father, and he dreams about his son named after me. I will see that he's named after me. And he says all the wonderful things that he's planning for his son until something happens at the end. And it is incredibly powerful. One of the greatest of all of the Rodgers and Hammerstein's songs. So we'll see you next time.
Bill. My boy Bill, I will see that he's named after me. I will. My boy Bill, he'll be tall and as tough as a tree. Bill, like a tree, he'll grow with his head held high and his feet planted firm on the ground. And you won't see nobody dare to try to boss him or toss him around. No pot-belly, baggy-eyed bully will boss him around. And I don't give a damn what he does, as long as he does what he likes. He can sit on his tail or work on a rail with a hammer and spikes. He can ferry a boat down the river, or pedal a pack on his back, or work up and down the streets of a town with a whip and a horse and a hack. He can haul a scow along a canal, run a cow around a corral, or maybe bark for a carousel. Of course it takes talent to do that well. He might be a champ of the heavyweights, or a fellow that sells you glue, or president of the United States. That'd be all right too. His mother liked that, but he wouldn't be president unless he wanted to be. Not Bill. My boy Bill, he'll be tall and as tough as a tree. Will Bill, like a tree, he'll grow with his head held high and his feet planted firm on the ground. And you won't see nobody dare to try to boss him or toss him around. No flat-bottom, flabby-faced, pot-belly, baggy-eyed bastard'll boss him around. And I'm damned if I'll marry his boss's daughter, a skinny-lipped virgin with blood like water. He'll give him a peck and call it a kiss, and look in his eyes through a lorgnette. Say, why am I carrying on like this? My kid ain't even been born yet. I can see him when he's 17 or so, and starting to go with a girl. I can give him lots of pointers, very sound, on the way to get round any girl. I can tell him, wait a minute, could it be? What the hell? What if he is a girl? Bill? Oh, Bill! What would I do with her? What could I do for her? Bum, with no money. You can have fun with a son, but you gotta be a father to a girl. She mightn't be so bad at that. A kid with ribbons in her hair, a kind of neat and petite little tin type of her mother. What a pair! My little girl, pink and white as peaches and cream is she. My little girl is half again as bright as girls are meant to be. Dozens of boys pursue her, many a likely lad does what he can to woo her from her faithful dad. She has a few pink and white young fellas of 2 and 3, but my little girl gets hungry every night, and she comes home to me. My little girl, I gotta get ready before she comes. I gotta make certain that she won't be dragged up in slums with a lot of bums like me. She's gotta be sheltered and fed and dressed in the best that money can buy.